Hi, science friends. Today I want to talk about resonance structures. Resonance structures, what they are is when you draw a Lewis structure, we've learned rules for drawing Lewis structures, and really the rules that I've taught you are how to draw the best Lewis structure. But sometimes you can draw Lewis structures that are not the best Lewis structure, but they're not really wrong. What they are is called resonance structures. So if you look at this diagram over here, this is a nitrate ion, NO3, with a -1 charge. These diagrams are all the same with the exception of the placement of the double bond. Most of them have they have two single bonds. They all have two single bonds and a double bond. The double bond, the oxygen's only going to have four valence electrons on it instead of the six because of the octet rule. But what these three structures are is they're called resonance structures. And so when you actually have a nitrate ion, it is kind of the average of these three resonance structures. So all of these are valid Lewis structures. I would accept them all correctly on an assignment, but they are all resonance structures. So resonance structures, as this says, differs only in the position of the electron pairs, never the atoms, okay? And I'll explain that a little bit more later. So how do we choose the best resonance structure? The best resonance structure is the one that reduces the formal charge. Now you're like, Miss Brown, what is formal charge? We're going to get to that in just a second. But it reduces the formal charge, okay? So let's talk about formal charge. Formal charge, you need to know this formula. You will not be given this on a test, so you do need to memorize this formula. It's found by taking the number of valence electrons, which you get by looking at the group number in the periodic table, and subtracting the total of number of lone pair electrons, that's your little dots that you've drawn in, okay, minus or plus in parentheses, so also minus, I guess, from the valence electrons, the number of bonds, okay? So a single bond is going to be counted as one bond, a double bond is going to be counted as two bonds, and a triple bond is going to be counted as three bonds. So that's what you're using when you get number of bonds. So let's work a few of these. Formal charge equals valence electrons minus, in parentheses, lone pairs plus bonds. So let's work a few of these to explain. So draw the resonance structures and determine the formal charge for the carbonate ion. Now, if you don't remember carbonate off the top of your head, if you pull out your ion sheet, Nathaniel, I'll have to give you one of these because I don't think I've given you one yet. You shouldn't need it for any of the other assignment, but the carbonate ion is CO3 with a -2 charge, okay? So if we were going to draw that, I just want you to draw it like you would a normal, like if I just ask you to draw the Lewis structure for the carbonate ion, okay? So to do that, carbon has 4 valence electrons, oxygen has 6 valence electrons, and there's 3 of those oxygens, so 6 times 3 is 18, 19, 20, 21, 22. We're going to have 22 total valence electrons that we have to put in our Lewis structure. So when we draw this, we'll have a carbon, and we're going to put some oxygens around it and give them some electrons. And I think if we draw this one correctly, we're going to have it like this. So we've got 2, 4, 6, 8. You can put those in the bond if you want to count them, do them that way and make it easier to kind of see them, to count them. Oh, and then we've got a -2 charge, so we're actually going to get 2 more there. So sorry about that. 24 valence electrons. Whoops. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 20, 22, 24, if I can count. I think that's right. 24 valence electrons. So that is one option of the carbonate ion, okay? Now, we could also draw that where our double bond goes up and our single bonds go out to the side. And we could also draw that where our double bond goes down and our single bonds go out to the side. And fill in all of our electron dots there. So those are going to be the 3 possible resonance structures for the carbonate ion. Making sure that the one that gets the double bond, you're only putting 4 valence electrons on it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, 24 total valence electrons. Now, let's go back to this idea of formal charge. Formal charge is the number of valence electrons minus the lone pair electrons plus the bonds. We find formal charge for every atom in the Lewis structure. Okay, so let's start with this carbon. Carbon has, wish I could change my pen color, but I don't think I can. Oh, maybe I can. Maybe I can't. Oh, yes. Okay, carbon has 4 valence electrons. Okay, here it is making 1, 2, 3, 4 bonds and doesn't have any lone pairs, any extra electron dots on it. So its formal charge is going to be 0. Okay? Let's look at this oxygen. Oxygen has 6 valence electrons minus, it doesn't have any, or it has, 1, 2, 3, 4, 5, 6 lone pairs and 1 bond. 6 plus 1. So 6 minus 6 plus 1, 6 minus 7, it's going to have a -1 formal charge. Okay? If we go on and do this oxygen, it has 6 valence electrons. It has 1, 2, 3, 4 lone pairs on it, plus 1, 2 bonds. So its formal charge is 0. Okay? This oxygen here is going to have the same formal charge as this one because they are identical basically in structure. Okay? So we need to do that for all of them. If you look at the structures, they're all basically going to have the same formal charge on different atoms. These that have a single bonded oxygen are going to have a -1 formal charge. So this one will have -1, this one will have -1, this one will have -1, this one will have -1. All the carbons are going to have a 0 formal charge like this one. So this one will have a 0 and this one will have a 0. And all of the oxygens that are double bonded, like this guy, are going to also have a 0 formal charge. All right. So in this resonance structure, the formal charges are all the same. So none of these are considered to be more stable than the other. Okay. So for this one, we did draw 3 resonance structures, but none of them are more stable than the other. That's why I told you if I'd asked you to draw this on an assignment yesterday before you learned about resonance structures and formal charge, each one of you may have drawn the double bond in a different place and it would have all been perfectly correct because all of those are the best structure and the best way to draw that compound. Okay? And this is just a diagram of that. The 3 Lewis structures, the different bonds in the different locations, they kind of drew theirs out as a tripod, and that was fine. They indicated the ones that had a negative formal charge. These, they didn't put a charge on it because the formal charge was 0. And so they all are equal resonance structures. Okay, so that's just that's a cleaner version of the answer there if you're copying that down and you couldn't follow my chicken scratch. So let's go on. Let's see if you can do one. So pause my video and then see if you can draw these for CO2 and calculate the formal charge for each. And then tell me which structure is most stable. So pause and draw and then resume when you're ready. All right, so you should have drawn your structures that look like this. Had you have done this assignment yesterday before we talked about formal charge, I hope that you would have drawn a structure like the first one. That one, carbon has 4 bonds like we talked about. The oxygen has double bonds, and everybody's completing their octet. Okay? However, this second one and this third one are also ways that you could draw that. They all do have a complete octet, but they just don't really go with the rules that I told you that are kind of the preferred structure rules. The oxygen liking to double bond, the carbon liking to form 4 bonds, and those kind of things. So this one, if you calculate the formal charge, and I'm going to walk through that again on these just as an example, this one is going to have the best formal charge. So this is the preferred structure, okay? These still have, that would I guess be the next preferred structure, but we're really just looking for the best one. We're looking for the one that has the most number of zeros for a formal charge, and that's going to be the best structure. The formal charge here were much higher. So this is going to be our preferred structure. So let's walk through and talk about these formal charges again. Let's use number 3 as an example. So let's talk about this first carbon. Carbon has 4 valence electrons. Then we subtract the number of dots that it's got on it, 1, 2, 3, 4. And then the number of bonds that it makes. So it's making 2 bonds. And so that's where we got the -2 formal charge. Let's look at this oxygen here. Oxygen has 6 valence electrons. It has no dots on it, so it's going to be 0 for lone pairs. But it has 1, 2, 3, 4 bonds. So 6 minus 4, it had a 2 for a formal charge. This other oxygen has 6 valence electrons. It has 4 dots on it. And it made 2 bonds. And so that gave that one that 0 formal charge. Okay? Now, you should have also calculated these other formal charges. I'll go ahead and do this one more as an example. This oxygen has a 6 valence electrons. It has 2 dots on it. And it has 3 bonds. So 6 minus 5, that would be a +1. So that's where we get that. Okay? So hopefully you're understanding formal charge a little bit better there. Now, let me give you one more example or one more thing to know about formal charge. Let's say that these were also a -1. I don't know. Let's say this was a -1 and a +1, and this was, I'm going to change some of these just to use an example. 0, all right, let me use another example with formal charge. I want to clear these formal charges out. Just as an example, these numbers that I'm going to write here are not correct formal charges, so make sure you know that. But I want to do this as an example. Let's say this was a +1 formal charge, the carbon was a -1, and the O was a 0. This one was a -1, this one was a +1, and this one was a 0. Okay? So let's say those were the structures that we drew in our formal charge. That's not correct, but let's do this for comparison's sake. How do we decide which of these two is the best resonance structure? Okay? They both have 1 0. They both have a +1 and they both have a -1. So how can we compare those and say which one's better? You always want your negative to be on the most electronegative element. Okay? The most electronegative elements on the periodic table are to the top and the right. Fluorine is the most electronegative element. Those noble gases on the very end don't count. They're not electronegative. They're stable. Okay? But fluorine, this is our periodic table, hydrogen, fluorine. Fluorine is going to be the most electronegative element. So the one closest to fluorine is the one you want to have the negative charges on it. So let's look at our negative charge. We're comparing carbon to oxygen. Which of those is most electronegative? Well, oxygen is most electronegative. It's closest to fluorine, closer than carbon, and so this would be the best resonance structure. There's one on your assignment that's going to use that information. Okay? All right. Now, the last thing I want to talk about today is the exceptions to the octet rule. You have another worksheet that's about these exceptions. So, some atoms are going to have less than 8 electrons. Let's look at this one for a minute down here, BH3. I've actually got it drawn down here, BH3. B has 3 valence electrons. H has 1 valence electron. So total valence electrons, 3 plus 1 times 3 hydrogens, is going to give us 6 valence electrons. You cannot fill that octet. You can't make 8 to fill an octet when you only have 6 valence electrons. That is the best structure to draw for that, though. And so it is an exception to the octet rule because it doesn't fill or satisfy the octet, but it is the acceptable best structure, the best way to draw that. Okay, so that's one exception. Another exception is if you have a compound that has an odd number of valence electrons. So let's say you had NO, nitrous oxide. Nitrogen has 5, oxygen has 6. Okay, so total we're going to have 11. It doesn't matter how you put those, you're going to have one guy that doesn't have a buddy. Okay, he can never make a bond. Bonds have to have 2 electrons. So when you draw this out, I don't exactly know what this Lewis structure looks like, but when you draw this out, 11, 6, 8. This is what it's going to look like. Ignore that. That's not a dot. Okay. That's what that would look like. Okay. 2, 4, 6, 8, 10, 11. Now, why did I put the single dot on the nitrogen instead of the oxygen? I did that because the odd number came from the nitrogen. Okay, so this is the best electron there. Ignore that X. That's not supposed to be there at all. I fudged and I couldn't fix it. I'll probably fix it. Oh, never mind. Screwed that up. Oh. Anyway. Okay, that is the best way. All right, we put the single dot on the nitrogen because the nitrogen's the one that has the odd number. Okay, that is the best way to do that, though. It doesn't satisfy the octet rule, but it comes as close as we possibly can. Oxygen has 8 electrons, nitrogen has 7, and that's the best that we can do there. Okay, so that's another exception to the octet rule. The last thing is an expanded octet. And an expanded octet, you have electrons, you have more electrons than you can hold. Okay, so there's one example on your homework where you have, I don't know what it is, PF5 or something like that. So you put your P in the middle and you put 5 things around it. We have not done any of those before, but sometimes that's how you do them. Okay, so there are some that would look like that. And you use all your electrons and you give dots to everybody. All right, and that's how you would feel it. That's called an expanded octet. Now, there are some other ones where after you use all the electrons, you still have some left over. And you have to put them on the middle atom. If you have extra electrons that you cannot use, you always put them on the middle atom. Okay? You have to make as many single bonds as possible, put all the dots on the outside, and then put any extra electrons on the middle atom. So there's some like that you'll see in your homework as well. So these are all exceptions to the octet rule, but they're doing them in the very best way possible. Okay? Now, let me rewind for just a second. Compounds like this guy, BH3, because he doesn't have any valence electrons here, there's nothing there, he would frequently like to bond with something like this that has 2 extra valence electrons that they need to share. And when they do, they form this bond here. This bond is called a coordinate covalent bond. It's covalent because electrons are shared. I don't really know what coordinate means, but it doesn't really make sense in the context. But what it means is that both of the electrons came from nitrogen. It means that this BH3 didn't really contribute to this relationship here. But that kind of bond where both of the electrons come from one element or one party rather than the other is called a coordinate covalent bond. Okay? So I think that wraps us up for the day. You all have the one worksheet, formal charge on one side, incomplete and expanded octets on the other side. Y'all reach out and ask questions if you have any. Have a great day.